Proportions. A proportion can be a really useful effect size measure, and it can be applicable when we have merely categorical or nominal data, none of this fancy interval data stuff. Here we are at the one proportion page. I can adjust so I get a proportion of 0.8, 16 out of 20, 80%. I can change any percentage into a proportion, any proportion into a percentage. And descriptively, this can be just about anything. So I can say the cloud cover in the sky at the moment is 80%, or 0.8. Proportion 0.8 of the sky is cloudy. And that's a perfectly good descriptive statistic. But if we want to do inference, if we want to draw conclusions from a sample to a population, I need to be more demanding, and I need to require that my proportion is the ratio of two frequencies, where x is the count of something and 20 a total count. So for example, I might have taken a test with 20 items and I got 16 of the 20 items correct, so my proportion correct is 0.8. The idea of being able to use an effect size descriptively, but then requiring more assumptions if we want to use it inferentially, is familiar from correlation and regression. So for correlation, think back to R for correlation. You can calculate R for just about any scatter plot, although it only makes much sense if both y and x are interval measures. But if we want to do inference, we want to draw a conclusion about the correlation in an underlying population. If we want to regard our data set as a sample, then we need to assume random sampling from a population that has a bivariate normal distribution, quite a demanding assumption. Well, correspondingly with proportions, you can use a proportion or a percentage in numerous situations. You can say, well, I was asleep for roughly 80% of the night last night. And that's a perfectly good descriptive use of a proportion. However, for inference, we need to assume P is the ratio between two frequencies. And our statistical model is that the total number n, 20, is a random sample from some population of potential cases. So in my test example, a random sample of 20 items from an infinite number of items I could have had on my test, and 16 is the number of those 20 I got correct. And we need to assume also, part of our statistical model, that all of these 20 items are independent and they all have the same probability of my getting them correct, which in practice is probably a little unrealistic, but we may well be prepared to make the assumption, regarded as a reasonable assumption, close to reasonable anyway, and do our calculations. Now let's think about proportions. If I adjust x, you can see how the proportion P goes in discrete steps, of course, and I can label the possibilities with this line. So P in this case can only take those values. So there we are, 16 out of 20. This might be, for example, 16 of the 20 students in a random sample of students remembered to bring their coat on a day when the weather forecast was for rain. And we'd like to use this as an estimate of the proportion of students from the whole population from which we're regarding these 20 as a random sample who are likely to remember the coat on a rainy day. We'd like a confidence interval on this sample proportion, 16 out of 20. So the 0.8, which is our sample proportion, is the point estimate of the proportion remembering their coat in the whole population. And the 95% confidence interval, as illustrated, of course, in the figure, runs from 0.58 to 0.92, from 0.58 there up to about 0.92. Now, if we look at how the confidence interval changes as we change x, well, proportion, of course, is limited to fall between 0 and 1. And as we get up closer to 20, well, there we are. We've got a confidence interval, which, of course, is all on one side of the observed proportion of 20 out of 20, because you can't go more than a proportion of 1. And it's really very asymmetric up near the boundary, the ceiling of 1. And as it gets down to around 0.5, it gets longer and more symmetric. Does this ring a bell? Correlation R behaves similarly between its boundaries of -1 and +1. And if I go down to lower proportions, we get exactly comparable mirror image sort of observation of these confidence intervals. Now in the chapter, the single proportion example referred to the first pilot test in the Gunsfeld experiments. These are experiments investigating telepathy, would you believe? Surely that's a bizarre concept that telepathy might actually exist, but researchers looked at it. And in this study, 8 out of 22 of the participants responded correctly. And if they were just randomly guessing, you'd expect 25%, a chance of 1 in 4 on each item. So 8 out of 22 with a proportion of 0.36 was just a little above chance. But it's still a very long confidence interval, from about 0.2 up to about 0.6. So 0.25 is what you'd expect by chance. This result certainly doesn't provide any evidence at all against random guessing, because 0.25 is well within this 95% confidence interval. You could take a p-value approach and say, here is the null hypothesized value. I'll use this slider to bring it down to 0.25. There we go, 0.25, pi naught, the hypothesized proportion in the population, 0.25, if there was just random guessing, and the 95% confidence interval obviously includes that value, so we're not able to reject that as the null hypothesis, and in fact the p-value is around about 0.2, which is what you'd eyeball from this confidence interval, and where it falls in relation to the value 0.25, that is of particular interest. As usual, the 95% confidence interval is totally informative, and really the p-value adds nothing.